The closest star to our Sun is not a single star. It is 3 stars bound together by gravity, and the nearest of them sits just 4.25 light-years away. That might sound far, but in the context of a galaxy that stretches 100,000 light-years across, it is essentially next door. And yet, despite that cosmic proximity, we still do not know whether any of those 3 stars host a world capable of supporting life. That is the central puzzle of the Alpha Centauri system. It is the most studied stellar neighborhood beyond our own, and it continues to surprise us with every new observation. Let us start with what we actually know. The Alpha Centauri system contains 3 stars. 2 of them, called Alpha Centauri A and Alpha Centauri B, orbit each other closely enough that from Earth, they appear as a single bright point of light to the naked eye. The 3rd star, Proxima Centauri, is a dim red dwarf orbiting much farther out and is technically the closest of the 3 to our Sun. Earth has been broadcasting radio signals into space for roughly 100 years. Those signals have already washed over dozens of stellar systems, including stars like Arcturus, which lies 37 light-years away, and Aldebaran, which sits about 65 light-years out. Alpha Centauri received our first radio signals decades ago. Whether anyone or anything has been listening is a different question entirely. Alpha Centauri A is the largest, most massive, and brightest member of the trio. It belongs to the same class of stars as our Sun, what astronomers call a main sequence star, meaning it fuses hydrogen into helium in its core as its primary energy source. Its mass is about 108% that of the Sun, and its radius is roughly 1.22 times larger. Even though it shares a similar surface temperature and spectral classification with our Sun, it radiates approximately 1.5 times as much energy overall. No planets around Alpha Centauri A have been confirmed. However, in 2021, researchers observing the star in infrared wavelengths found intriguing hints of a possible planet-like object nearby. Preliminary estimates suggested its mass could range anywhere from 9 to 35 Earth masses, and its radius might be between 3.3 and 7 times that of Earth. It would orbit about 1.1 astronomical units from Alpha Centauri A, meaning it sits at roughly the same distance from its star as Earth does from our Sun, and it would complete 1 full orbit in approximately 1 year. 1 astronomical unit, for context, is the average distance between Earth and our Sun, about 150 million kilometers. Using that as a measuring stick helps translate cosmic distances into something more concrete. The detection of this candidate object relied on thermal infrared data, which picks up heat signatures rather than visible light. The James Webb Space Telescope and certain ground-based observatories are capable of following up on observations like these, but as of the current state of research, additional confirmation is still needed before this object can be classified as a confirmed planet. Alpha Centauri B, also known by its traditional name Ptolemy, is the 2nd major star in the system. It is a main sequence star like its companion, but noticeably smaller and cooler. Its mass is roughly 90% that of the Sun, and its radius measures about 86% of the Sun's. Its surface temperature is approximately 5,260 Kelvin, which works out to slightly under 5,000 degrees Celsius. That cooler temperature gives it a distinct orange hue when viewed through instruments sensitive to color. Because of its lower temperature, Alpha Centauri B is also significantly less luminous than our Sun. On average, it puts out about half the light our star does. Interestingly, it is unusually active in X-ray emissions compared to other stars of its class, and it displays pronounced surface flares and matter ejections, making it a somewhat energetic and volatile object in certain respects. In 2012, a team of astronomers from the Geneva Observatory proposed that a planet existed very close to Alpha Centauri B, with an orbital period of roughly 12 days, which would place it extremely close to the star, far closer than Mercury is to our Sun. Its radius was estimated to be slightly smaller than Earth's. The announcement generated significant excitement because it would have been the closest known exoplanet to our solar system. However, 3 years later, in 2015, an independent analysis revealed a mathematical error in the original data processing. When the error was corrected, the signal attributed to the planet disappeared. The planet's existence was ruled erroneous. This kind of rigorous self-correction is standard in astronomy. A signal that looks promising often requires years of follow-up and independent verification before it can be accepted as real. The two main stars, Alpha Centauri A and B, orbit each other in a slightly elongated elliptical path. One full orbit takes approximately 80 years to complete. During their orbit, the distance between them varies considerably. At their closest approach, they are separated by about 11.2 astronomical units, roughly the distance between our Sun and Saturn. At their farthest separation, the distance stretches to about 35 astronomical units, comparable to the distance between our Sun and Neptune. The center of mass around which both stars orbit lies at roughly 4.36 light-years from our Sun. To put that into perspective, 1 light-year equals approximately 9.46 trillion kilometers. So the Alpha Centauri AB pair is about 41 trillion kilometers away from us. Now we arrive at the most scientifically productive member of the system, Proxima Centauri. Proxima is a red dwarf, a class of star that is far smaller, cooler, and dimmer than our Sun. Its mass is only about 12% that of the Sun. Its physical size is approximately 7 times smaller than our Sun. Its surface temperature is just barely above 3000 Kelvin, and its luminosity is a mere 0.17% of the Sun's output. Despite all of that, Proxima is the record holder in one crucial respect. It is the closest known star to our solar system, sitting 4.25 light-years away, slightly closer than the Alpha Centauri AB pair at 4.36 light-years. Its Latin name reflects this status. Proxima means nearest. Proxima Centauri is also slowly approaching our solar system. In approximately 26,700 years, it will be only slightly more than 3 light-years away, making it even closer than it is today. But from a human perspective, this kind of motion is imperceptibly slow. We have no way to watch it happen in real time. Because of its low luminosity, Proxima Centauri cannot be seen from Earth with the naked eye. You need a telescope to find it, even though it is literally the nearest star to our Sun. Its distance from its 2 companion stars is substantial. Currently, Proxima sits about 13,000 astronomical units away from Alpha Centauri A and B. That translates to roughly 0.21 light-years. Models project that over the next 300,000 years, that gap will gradually shrink to about 4,100 astronomical units as the orbit progresses. The entire orbital period for Proxima around the system's common center of mass is estimated at 547,000 years. Despite its dimness, Proxima Centauri is scientifically the most exciting member of the trio because it hosts confirmed exoplanets. The first confirmed planet, designated Proxima Centauri B, was detected in 2016 using the radial velocity method. This technique works by measuring tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. A planet tugs its star slightly toward it as it orbits, and that motion produces a measurable Doppler shift in the star's light. 4 years later, in 2020, the existence of Proxima Centauri B was independently confirmed using spectrographic analysis performed with the Very Large Telescope, one of the most powerful ground-based observatory systems on Earth. The Very Large Telescope uses an array of large mirrors working in concert to achieve extraordinary resolution and sensitivity. According to current estimates, Proxima Centauri B orbits just 0.05 astronomical units from its host star. To give that number meaning, consider that Mercury, the innermost planet in our solar system, orbits at about 0.39 astronomical units from the Sun. Proxima B is more than 7 times closer to its star than Mercury is to ours. Despite that extreme closeness, Proxima Centauri B may not be scorching hot. Because Proxima itself is so dim, it radiates far less energy than our Sun. Proxima B receives roughly 1.5 times less thermal energy from its star than Earth receives from the Sun. Its estimated average temperature is about 234 Kelvin, which works out to -39 degrees Celsius. That is quite cold, but it raises the possibility that under the right atmospheric conditions, liquid water might exist in localized regions, particularly on the day side of the planet. The orbital period of Proxima B is roughly 11 Earth days. That close orbit has another major implication. A planet orbiting that close to its star for billions of years would almost certainly become tidally locked. Tidal locking occurs when the gravitational forces between a planet and its star synchronize the planet's rotation with its orbital period. The result is that one side of the planet perpetually faces the star in permanent daylight, while the opposite side remains in permanent darkness. On a tidally locked world, the temperature extremes between the day side and night side would be severe. The sunlit hemisphere could be warm enough for liquid water in some regions. The dark hemisphere could be frozen solid. A thick, dense atmosphere could theoretically transport heat from the day side to the night side, smoothing out the temperature gradient and making broader regions more habitable. But whether Proxima b has such an atmosphere, or any atmosphere at all, remains unknown. The bigger threat to any potential atmosphere on Proxima b comes from the star itself. Proxima Centauri is a flare star, meaning it regularly erupts with intense bursts of energy. These flares release X-ray and ultraviolet radiation, and they also hurl charged particles into space at high velocities. For a planet sitting as close as Proxima b does, that bombardment could be relentless. Over geological timescales, this stellar activity might gradually strip away any atmosphere the planet had accumulated. The solar wind from our own sun has a similar effect on Mars, which has a very thin atmosphere partly because of billions of years of exposure to the sun's particle stream. Mars has a weak magnetic field and no significant magnetic protection. If Proxima b lacks a strong magnetic field, its atmosphere would face the same fate, or potentially a more severe one, given how active Proxima is. A strong planetary magnetic field could offer meaningful protection. Our own Earth benefits from a robust magnetic field generated by its iron core, which deflects the solar wind and shields our atmosphere. Whether Proxima b has a similarly protective field depends on its interior structure and composition, neither of which we can currently measure directly. The second confirmed planet in the Proxima system, Proxima Centauri c, was confirmed in 2020. It is a very different world from its inner neighbor. It orbits roughly 1.5 astronomical units from Proxima Centauri, which is a much wider orbit than Proxima b. One full orbit takes slightly over 5 Earth years. Its mass is estimated at somewhere between 6 and 8 times that of Earth. Depending on its actual size and density, it would likely fall into one of 2 planet categories. If it is relatively compact and rocky, it would be classified as a super-Earth. If it is larger and more gaseous, it would fall into the mini-Neptune category. The radius has not yet been precisely determined. At 1.5 astronomical units from such a dim star, Proxima c is extremely cold. Its surface temperature is estimated at around 39 Kelvin, which is approximately -234 degrees Celsius. That is a frigid, inhospitable environment by any measure. One of the more intriguing findings about Proxima c is that some observations suggest it may have a ring system with a radius roughly 5 times that of Jupiter. If confirmed, this would make Proxima c a ringed planet in another stellar system, which would be a remarkable discovery. However, this remains tentative and awaits more thorough observational confirmation. Beyond these 2 confirmed planets, observations using the Very Large Telescope have hinted at a third, much smaller body orbiting extraordinarily close to Proxima Centauri. This candidate object would sit just 0.029 astronomical units from the star, even closer than Proxima b. Its mass is estimated at roughly 25% that of Earth, making it a small, rocky world if it exists. On this object, a full year would last only about 5 Earth days. The surface temperature could reach approximately 360 Kelvin, which is about 87 degrees Celsius. At that temperature, liquid water on the surface would be unlikely under normal pressure conditions, though subsurface or atmospheric scenarios could differ. Whether this third body is real remains to be established. Independent confirmation is needed, and the history of exoplanet research is filled with candidate detections that did not survive further scrutiny. The Alpha Centauri system as a whole sits about 40 trillion kilometers from Earth. That is 40 million kilometers. Light crosses this distance in roughly 4 years and 4 months. Any radio signal we send in that direction will take over 4 years to arrive. Any response would take another 4 years to return. A two-way conversation would have, at minimum, a delay of over 8 years. For any physical spacecraft, the challenge is staggeringly greater. Our fastest space probes to date, including the Voyager spacecraft, travel at roughly 60,000 kilometers per hour. At that speed, reaching the Alpha Centauri system would take approximately 70,000 years. No current propulsion technology comes remotely close to cutting that journey to a human-relevant timescale. One proposal that has received serious scientific attention is the Breakthrough Starshot program. The concept involves launching a fleet of thousands of tiny probes, each no larger than a few centimeters across. These probes would be equipped with extremely thin, lightweight sails made of highly reflective material. A powerful laser array, located on Earth, would fire concentrated pulses of light at the sails, using the pressure of photons to accelerate the probes. The estimated terminal velocity of such probes would be approximately 20% of the speed of light. At that speed, the journey to Proxima Centauri would take roughly 20 years. An additional 4 to 5 years would be required for the data the probes collected to travel back to Earth using radio signals. So in total, a mission launched in the coming decades could potentially return its first data sometime around mid-century or early in the second half of the century. The technical hurdles are considerable. The laser array would need to be built at a scale far beyond anything currently existing. The sails would need to withstand intense radiation without degrading. The probes would need to operate autonomously and gather scientifically useful data during a brief flyby of the target system, since they would be traveling too fast to slow down and enter orbit. And the entire system would need to maintain precision alignment over vast distances. None of these problems are considered theoretically impossible. They are engineering challenges, not violations of physical law. But moving from concept to reality will require decades of technological development and enormous investment. In the meantime, we observe. Ground-based and space-based telescopes continue to refine our understanding of the Alpha Centauri system. The Very Large Telescope has already played a central role in confirming the planets around Proxima and gathering high-resolution spectroscopic data on all 3 stars. Newer instruments and observing campaigns are expected to constrain the properties of known planets more precisely and potentially reveal additional objects. The James Webb Space Telescope has the sensitivity to potentially detect the infrared signatures of large planets around Alpha Centauri A and B if they exist. It can also analyze the light passing through exoplanet atmospheres to search for chemical signatures of molecules like water vapor, carbon dioxide, methane, and oxygen. Those molecules are associated with biological and geological processes on Earth, and their presence in an exoplanet's atmosphere would be a meaningful clue about surface conditions. A dedicated telescope called Ptolemy, named after the traditional designation of Alpha Centauri b, was in development specifically to hunt for Earth-sized planets in the habitable zones of Alpha Centauri A and B. The habitable zone is the range of orbital distances where temperatures could allow liquid water on the surface of a rocky planet, given the right atmospheric conditions. Detecting small planets in that zone would be an extraordinary scientific achievement. The Alpha Centauri system represents a unique convergence of scientific interest. It is close enough to study in extraordinary detail. It contains multiple stars with different properties, offering varied environments. It has at least 2 confirmed planets and possibly more. And it sits at the edge of what might someday be achievable for interstellar exploration. What we do not yet know fills more pages than what we know. We do not know whether any planet in the system has a stable atmosphere. We do not know whether liquid water exists anywhere in the system. We do not know whether Proxima b has a magnetic field capable of protecting potential biosignatures. We do not know the true size of Proxima c, or whether its ring system is real. We do not know whether the candidate objects around Alpha Centauri A or the innermost candidate around Proxima are genuine planets. Each of these unknowns corresponds to an active area of research. Radial velocity surveys continue. Infrared imaging campaigns are being refined. Astrometric measurements using satellites capable of detecting tiny shifts in star positions are providing new constraints. And dedicated mission concepts for eventual probes to the system are progressing through early planning stages. What is remarkable is how much we have learned in just the past decade. The first confirmed exoplanet around any of these 3 stars was announced in 2016. In under 10 years, we went from 0 confirmed planets in the closest stellar system to humans, to at least 2 confirmed planets and multiple intriguing candidates. The detection methods have improved, the instruments have grown more sensitive, and the scientific community has built a much clearer picture of what this system actually contains. The Alpha Centauri system is not a distant abstraction or a theoretical placeholder. It is a real cluster of stars, with real planets, real magnetic activity, real infrared signatures, and real physical complexity. It is a place with its own weather, its own stellar cycles, its own gravitational dynamics, and potentially its own geology. For the first time in human history, we are able to ask meaningful scientific questions about the nearest stars and expect answers to emerge within our lifetimes. That is not a trivial development. It represents a fundamental expansion in what is knowable about the universe. From where we stand, the 4.25 light-years separating us from Proxima Centauri have not gotten any smaller. But our ability to reach across that distance with our instruments, our models, and eventually our machines grows steadily more capable with each passing year. To understand why the Alpha Centauri system captivates astronomers so deeply, it helps to understand the broader context of stellar astronomy and what we mean when we talk about nearby stars. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. They are not evenly distributed. Most cluster toward the galactic center, which is roughly 26,000 light-years from our Sun. In our local region of the galaxy, stars are spread much more thinly, with an average separation of several light-years between neighboring systems. The stellar neighborhood, within about 15 light-years of our Sun, contains only about 50 known stars and brown dwarfs. Most of these are dim red dwarfs, invisible to the naked eye, detectable only through telescopes. A handful of brighter stars make the list, including Sirius, the brightest star in the night sky from Earth's perspective, which sits about 8.6 light-years away. But none of these come closer than the Alpha Centauri system. This concentration of scientific attention on Alpha Centauri is not just sentimentalism about proximity. It reflects a genuine principle of astrophysics. Closer objects are easier to study in detail. The same telescope that can detect a broad signature of a star 80 light-years away can resolve fine spectroscopic features of a star 4 light-years away. The same instrument that can confirm a gas giant around a distant star might detect a rocky planet around Alpha Centauri. Distance matters enormously in observational astronomy. The history of attempts to resolve the details of Alpha Centauri goes back centuries. Ancient peoples in the southern hemisphere, where Alpha Centauri is visible, observed the star and gave it names. The system is not visible from most of the northern hemisphere. From latitudes north of about 29 degrees north, it remains below the horizon. For most of recorded Western astronomical history, Alpha Centauri was known mainly through navigational records and the accounts of explorers who traveled south. The first serious attempts to measure the distance to Alpha Centauri came in the 19th century. In 1838, Scottish astronomer Thomas Henderson used the method of stellar parallax to estimate the distance. Parallax works by observing how a nearby star appears to shift its position slightly against the background of distant stars, as Earth moves from one side of its orbit to the other over the course of 6 months. The angular shift is tiny for even nearby stars, and measuring it required extraordinarily careful instrumentation by the standards of the time. Henderson's measurement was among the first successful parallax measurements of any star beyond the Sun. He calculated a distance that was roughly in the right range, though subsequent more precise measurements refined the value considerably. Today, satellite-based astrometry from missions like Hipparcos and Gaia has measured the distances to nearby stars with extraordinary precision. The current accepted distance to the Alpha Centauri AB pair is 4.36 light-years. Proxima Centauri sits at 4.245 light-years. These numbers carry uncertainties measured in the thousands, not the tenths, of light-years, meaning we know the distance with remarkable precision. The question of whether Proxima Centauri is gravitationally bound to Alpha Centauri A and B, or whether it is merely a passing star that happens to be nearby right now, was debated for many years. Careful analysis of the star's motions and velocities eventually established that all three are almost certainly gravitationally bound in a very wide orbit. Proxima orbits the center of mass of the system, but at such an enormous distance and with such a long orbital period that earlier observers had difficulty distinguishing a bound companion from an unrelated neighboring star. The orbital dynamics of the inner pair, Alpha Centauri A and B, were worked out in considerable detail during the 20th century. Knowing their separation, masses, and orbital eccentricity allows astronomers to calculate their mutual gravitational influence with high precision. That precision matters for exoplanet searches because any planet in the system must maintain a stable orbit in the gravitational environment created by multiple stellar bodies. In a system with two closely orbiting stars, planetary stability is a nuanced problem. Planets can exist in one of two configurations. They can orbit tightly around just one star, well within the gravitational sphere of influence of that star and unperturbed by the companion. Or they can orbit both stars together in a wide orbit that encompasses the entire stellar pair. These are called circumbinary orbits. For Alpha Centauri A and B, simulations suggest that planets in stable orbits around either individual star would need to remain within roughly 3 astronomical units of that star. Beyond that, gravitational perturbations from the companion would become large enough to destabilize orbits over geological timescales. This constraint makes the habitable zone particularly interesting. For Alpha Centauri A, with its slightly greater luminosity than our Sun, the habitable zone sits roughly between 1 and 1.4 astronomical units. That is comfortably within the stable orbital range. For Alpha Centauri B, which is cooler and dimmer, the habitable zone sits closer in, between about 0.5 and 0.9 astronomical units. That too falls within the range where stable orbits are possible. In other words, from a theoretical standpoint, both Alpha Centauri A and B could host rocky planets in their habitable zones, and those planets could maintain stable orbits over billions of years. Whether such planets actually formed, survived, and retained atmospheres is a different and more complex question. Planet formation in binary star systems is thought to be more challenging than in single star systems like our own. During the early stages of solar system formation, a disk of gas and dust, called a protoplanetary disk, surrounds the young star. Planets grow by accretion, with smaller particles sticking together into larger aggregates that eventually sweep up enough material to form planetary bodies. In a binary system, the gravitational influence of the companion star stirs up the material in the protoplanetary disk. Particles that would otherwise gently collide and stick together may instead be moving at high relative velocities when they meet, causing them to shatter rather than accrete. Computer simulations of planet formation around Alpha Centauri A and B have given mixed results over the years, with some models suggesting planets can still form successfully, and others suggesting the binary interaction suppresses planet formation significantly. The fact that no confirmed planets have yet been found around Alpha Centauri A or B does not definitively resolve this question. Absence of evidence is not the same as evidence of absence, particularly when our detection methods still have limitations. Small rocky planets in the habitable zone of Alpha Centauri A or B would be extremely challenging to detect with current technology. Their gravitational signature on the star is tiny. Their transits, if they happen to pass in front of the star from our line of sight, would be brief and require years of continuous monitoring to catch. The dedicated Ptolemy telescope mission was designed with this specific challenge in mind. By targeting the Alpha Centauri system with a specialized instrument optimized for detecting the tiny wobbles associated with Earth-sized planets, the mission aimed to either find such planets or rule them out to a high degree of confidence. That kind of definitive constraint would itself be scientifically valuable, because it would tell us something about whether the conditions for Earth-like planets exist in the most accessible stellar neighborhood. Red dwarf stars like Proxima Centauri deserve special attention in the discussion of potentially habitable exoplanets, not only because of Proxima's proximity, but because of a broader statistical fact about the galaxy. Red dwarfs are by far the most common type of star in the Milky Way. They make up roughly 3/4 of all stars. If red dwarfs cannot host habitable worlds, then the prospects for life in the galaxy are significantly constrained. If they can, then the galaxy may be teeming with potentially life-friendly environments. The challenge with red dwarf habitability is multifaceted. First, the habitable zone of a red dwarf is very close to the star. Because red dwarfs emit so little light, a planet must orbit very close to receive enough warmth to maintain liquid water on its surface. That proximity almost guarantees tidal locking, as we discussed in the context of Proxima b. Second, red dwarfs are frequently magnetically active, particularly when they are young. Flares from red dwarfs can be disproportionately energetic relative to the star's overall luminosity. A flare that would be unremarkable from a sun-like star can be catastrophic for a planet orbiting close to a red dwarf, stripping away atmospheric gases and bathing the surface in intense ultraviolet and X-ray radiation. Third, because red dwarf habitable zones are so close in, planets there have shorter orbital periods. A planet completing an orbit in 11 days, like Proxima b, has experienced far more orbits in the history of the system than Earth has around the Sun. Each orbit exposes it to radiation, stellar wind, and gravitational stresses. On the other hand, there are reasons to think red dwarfs might not be universally hostile to life. Red dwarfs have extremely long lifespans. Where our Sun is expected to remain on the main sequence for a total of about 10 billion years, a red dwarf of Proxima's mass may remain stable for trillions of years. That is a timescale almost incomprehensibly longer than the current age of the universe. Life on Earth required billions of years to develop complexity. Given enough time, even a slowly habitable environment might eventually host biology. Also, the severity of flare activity on red dwarfs tends to diminish as the star ages. A young red dwarf may flare intensely and frequently. An older one settles into a calmer pattern. Proxima Centauri is estimated to be approximately 4.85 billion years old, making it slightly older than our own Sun. Whether it has calmed sufficiently over its lifetime to allow atmospheric retention on nearby planets is a question current research is actively trying to answer. The search for atmospheres on Proxima b and other nearby exoplanets is one of the most technically demanding problems in contemporary astronomy. To detect an atmosphere, researchers typically look for the light that passes through it when a planet transits its star. The star's light is filtered by the atmospheric gas, and different molecules absorb different wavelengths. By comparing the spectrum of the star's light during a transit to the spectrum outside of transit, scientists can in principle identify atmospheric components. This technique, called transmission spectroscopy, has been used successfully on larger planets around more distant stars. For a planet as small as Proxima b, which is only slightly larger than Earth, the atmospheric signal would be extremely faint. And Proxima b's orbital geometry means it does not transit its star from our viewing angle, which eliminates the direct transit spectroscopy approach entirely. Alternative observational methods exist. When a planet is on the far side of its star from Earth, the star briefly blocks the planet's own emitted and reflected light. By comparing the brightness before, during, and after this occultation, researchers can constrain properties of the planet's emission. This technique has also been applied to characterize exoplanet atmospheres, though again the signal for a small rocky world is extremely faint. Future space telescope missions designed specifically for direct imaging of exoplanets represent the next frontier. The concept involves using a starshade, a precisely shaped occulter that flies in formation with a telescope and blocks the overwhelming glare of the parent star, allowing the much fainter reflected light of a nearby planet to be detected directly. Such a mission targeting Alpha Centauri would allow researchers not just to detect potential planets, but to study their light directly, looking for chemical signatures in their reflected spectra. One of the most significant discoveries in exoplanet science in recent decades is how common planets appear to be. Before the first confirmed detection of a planet around a main sequence star in 1995, the existence of planets around other stars was theoretical. Within a few years of the first discovery, planets were being found regularly. The Kepler Space Telescope, which monitored over 150,000 stars continuously for 4 years, found thousands of confirmed exoplanets and suggested that virtually every star in the galaxy has at least one planet. If that statistical result holds for our nearest stellar neighbors, it means Alpha Centauri A, Alpha Centauri b, and Proxima Centauri all likely have planets. What we do not yet know is whether any of those planets have the characteristics relevant to habitability, namely appropriate size, suitable temperature, liquid water, atmospheric pressure, and protection from radiation. The question of liquid water deserves special elaboration because it is so central to how we define habitability in the context of life as we understand it. All known life on Earth requires liquid water. This is not just a coincidence of our biochemistry. Water has unique physical and chemical properties that make it an extraordinary solvent and medium for biological processes. It dissolves a vast range of chemical compounds, allowing the complex molecular interactions that drive metabolism, reproduction, and genetics. Its liquid phase is stable over a wide temperature range under the right pressures. It moderates temperature extremes because of its high heat capacity, and it participates directly in countless biochemical reactions. Given these properties, the presence of liquid water is used as a proxy for biological potential when evaluating other worlds. Worlds that could maintain liquid water on their surfaces are said to fall within the habitable zone, also called the Goldilocks zone, where conditions are neither too hot nor too cold for liquid water. It is important to note that the habitable zone is defined in terms of surface liquid water under Earth-like atmospheric pressure conditions. A world outside the nominal habitable zone could still harbor liquid water underground, beneath a thick ice shell, or in other environments. Europa, a moon of Jupiter, is well outside our Sun's habitable zone, but maintains a liquid subsurface ocean because of tidal heating from Jupiter's gravity. Life does not necessarily require sunlight or a comfortable surface temperature. It requires energy and chemistry. This broader definition of habitability potentially expands the range of environments worth investigating, even within the Alpha Centauri system. Proxima c, despite its frigid estimated surface temperature, might have internal geological or tidal heat sources. Any moons orbiting large planets in the system could have their own thermal environments. These possibilities are speculative, but they illustrate how the concept of habitability is more nuanced than a simple distance calculation from a star. The detection of Proxima Centauri b in 2016 was made possible by a particularly sensitive spectrograph called HARPS, the High Accuracy Radial Velocity Planet Searcher. Installed on the European Southern Observatory's 3.6-meter telescope in Chile, HARPS measures stellar motion with extraordinary precision, capable of detecting velocity shifts as small as 1 meter per second. That is roughly the speed of a leisurely walking pace. For comparison, the orbital speed of Earth around the Sun is about 29.8 kilometers per second. The data for Proxima b was accumulated over many years of observation with a focused observing campaign called Pale Red Dot in 2016, contributing the final confirming observations. The campaign name was a nod to Carl Sagan's famous description of Earth as a pale blue dot when seen from the outer solar system. Proxima b, orbiting a red dwarf, was framed as a pale red dot. Espresso, the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, represents the next generation beyond HARPS. Installed on the Very Large Telescope in Chile, it achieves even greater precision. It was Espresso that provided the 2020 independent confirmation of Proxima b's existence and mass estimate. Each technological generation opens new possibilities for detecting smaller and more distant planets. The search for biosignatures, chemical signs of life, in exoplanet atmospheres is still largely aspirational with current technology. But with the James Webb Space Telescope operational and future large observatories in development, the field is moving toward the capability to characterize the atmospheres of nearby rocky worlds. The James Webb Space Telescope is optimized for infrared observations, which are particularly useful for studying the thermal emission of planetary objects and for identifying molecular absorption features in exoplanet atmospheres. While it was not designed primarily as an exoplanet characterization instrument, it has already demonstrated remarkable sensitivity in studying the atmospheres of exoplanets transiting their stars. The extremely large telescope, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters across. When completed, it will be the largest optical and near-infrared telescope ever built. Its capabilities for high-resolution spectroscopy and direct imaging of exoplanets will surpass anything currently in operation. It could potentially detect and characterize the atmospheric spectra of nearby rocky exoplanets, including those in the Alpha Centauri system, if conditions are favorable. The European Space Agency's Plato mission, designed to detect and characterize exoplanets around bright nearby stars, may also contribute to the study of Alpha Centauri in coming years. By studying stellar oscillations as well as planetary transits, Plato will provide detailed constraints on the ages, sizes, and compositions of target stars, which in turn improves the precision of planetary parameters derived from those systems. One of the deep ironies of the Alpha Centauri situation is that our best chance of learning whether the closest stellar system hosts habitable worlds may come not from sending anything there, but from building better instruments here. The investment in next-generation telescopes, spectrographs, and space observatories could answer fundamental questions about Alpha Centauri within decades, far sooner than any physical probe could arrive and return data. At the same time, The breakthrough starshot concept and similar proposals represent a genuinely new direction in space exploration philosophy. For the entirety of the space age, exploration has meant sending human astronauts or robotic spacecraft to destinations within our solar system. The distances involved range from the few 100,000 kilometers to the Moon to the roughly 20 billion kilometers to the outer reaches of the solar system visited by the Voyager probes. Interstellar distances are categorically different. The nearest star beyond the Sun is more than 2,000 times farther than Voyager has traveled in almost 50 years. The energy required to send even a small spacecraft at useful interstellar speeds is enormous. The breakthrough starshot approach attempts to sidestep this problem by making the spacecraft itself negligibly small, so that a powerful laser can accelerate it to a significant fraction of light speed. At 20% of light speed, a probe would cover the distance to Proxima Centauri in approximately 21 years. That is a physically achievable journey timescale. A mission launched sometime in the coming decades could return its first data before the end of this century. What such a probe would observe during its brief flyby of the Proxima system is a fascinating question. Traveling at 1/5 the speed of light, it would flash through the system in a matter of hours, with only that brief window to photograph planets, measure magnetic fields, sample the local stellar wind, and transmit data back to Earth. The science that could be done in those hours would depend entirely on how sophisticated a payload could be packed into a centimeter-scale device. Current thinking involves sensors capable of measuring magnetic fields, particle fluxes, optical imaging, and basic spectroscopy. The technological miniaturization required is extreme, but the direction is consistent with broader trends in computing and sensor technology. Electronics that once required room-sized installations now fit in a smartphone. The trajectory of miniaturization over several more decades might indeed enable gram-scale science payloads with meaningful capabilities. The communication challenge is also significant. A probe at Proxima Centauri, 4 light-years away, attempting to send data back to Earth, would need to transmit radio signals that travel for over 4 years before reaching us. The signal would be extremely faint by the time it arrived. The receiving infrastructure on Earth would need to be far more sensitive than current antenna arrays to detect such a whisper of data from interstellar distance. The breakthrough starshot collaboration has proposed using a laser communication system for the return link, as laser signals can be focused more tightly than radio waves, reducing the power required. Even so, receiving data from such a distance would require a very large receiving aperture and sophisticated signal processing. The planning and development timeline for such a mission is measured in decades. Significant engineering milestones remain ahead. But the fact that a credible scientific consortium is investing real resources into working through the problem is itself a historical development. Before breakthrough starshot, interstellar travel was largely confined to science fiction and theoretical papers. Now, it occupies conference halls and serious engineering discussions. Returning to what we know with more certainty, the Alpha Centauri system's stellar properties are some of the best characterized of any stars beyond our Sun. Their masses, radii, luminosities, ages, surface temperatures, magnetic activity levels, and chemical compositions have all been measured through decades of careful observation. Spectroscopic analysis reveals the chemical abundances in each star's atmosphere, which reflects the chemical composition of the cloud of gas and dust from which the stars originally formed. The Alpha Centauri stars show slightly higher abundances of heavier elements compared to our Sun, a property astronomers call metallicity. Stars with higher metallicity tend to form planetary systems more readily because the heavier elements are the raw materials from which rocky planets and the cores of gas giants are built. If this statistical correlation holds, it is actually a mild point in favor of the Alpha Centauri system having rocky planets. The age of the system is estimated at roughly 5 to 6 billion years, slightly older than our solar system, which formed about 4.6 billion years ago. This age is significant for habitability considerations. If life requires billions of years to develop, as was the case on Earth, then a 5 billion-year-old planetary system has had ample time for biology to emerge and evolve, if the conditions were otherwise suitable. The story of Alpha Centauri is ultimately a story about the frontier of human knowledge. It is the place where our direct experience of the solar system ends and the vast unknown of interstellar space begins. It is close enough to tantalize us with detail, but still far enough that we cannot yet resolve the fundamental questions about whether it hosts life or worlds like our own. Every observational advance of the past decade has revealed more complexity and more interest in this system than was known before. The discovery of Proxima b opened the possibility that the nearest stellar system hosts a planet of roughly Earth's mass in a temperate orbit. The tentative hints of additional objects around Alpha Centauri A and in the innermost regions of the Proxima system suggest that planet formation in this neighborhood is ongoing in some form. And the theoretical work on habitability, atmospheric stability, tidal locking, and magnetic field protection is producing increasingly specific predictions that future observations can test. The universe tends to reward sustained curiosity. Every technological generation discovers things about the cosmos that the previous generation considered unknowable. We live in a period when the nearest stars are transitioning from points of light to places with identifiable planetary companions. The next transition, identifying planets with atmospheres and eventually constraining whether those atmospheres contain signatures of chemistry associated with life, is within the horizon of current scientific planning. Alpha Centauri is not merely a neighbor by the standards of stellar astronomy. It is a target, a benchmark, and a test case for every method and instrument we are developing to understand our place in the universe. If we can answer the basic questions about this system, those answers will serve as proof of concept for applying the same methods to the hundreds of other nearby stellar systems and eventually to stars across the galaxy. The distance of roughly 40 trillion kilometers separating us from Proxima Centauri has not changed since our species first looked up at the night sky and wondered what those lights were. But the quality and depth of what we can now learn about those distant fires, without going there, grows measurably every year. And the plans to someday reach across that void, if not with people, then at least with fragments of our curiosity made into machines, have moved from imagination into engineering. That is where the story of Alpha Centauri stands, not at an ending, but at the very early chapters of a long and unfolding scientific investigation whose most significant discoveries almost certainly still lie ahead. To appreciate the full significance of the Alpha Centauri system, it helps to understand how our understanding of stars and stellar systems has evolved over the past 2 centuries, and how that evolution has shaped the specific questions we now ask about our nearest neighbors. For most of human history, stars were treated as essentially identical objects, differing mainly in their brightness and position in the sky. The ancient Greeks categorized stars by magnitude, a scale of apparent brightness still in use today in modified form. But the idea that stars were distant suns, objects fundamentally similar to our own star but vastly farther away, was slow to take hold. It was not until the Renaissance and the subsequent development of telescopic astronomy that the scale of stellar distances began to be appreciated. When stellar parallax was first successfully measured in 1838, it produced something remarkable, a quantitative confirmation that stars were individual, enormously distant objects, not celestial fixtures embedded in some nearby sphere. The measurement of Alpha Centauri's distance in that year by Thomas Henderson, alongside near-simultaneous measurements of other stars by Friedrich Bessel and Wilhelm Struve, established the first rung of the cosmic distance ladder. Every subsequent method for measuring astronomical distances ultimately anchors back to parallax for its calibration. Once distances to stars were known, their intrinsic luminosities could be calculated. Stars that appeared bright simply because they were close could be distinguished from stars that appeared bright because they were genuinely energetic. Conversely, faint stars might be nearby dim objects or distant brilliant ones. The ability to sort these cases out was the foundation of modern stellar astrophysics. By the early 20th century, astronomers had classified thousands of stars into spectral types based on the characteristic absorption lines in their spectra. These lines are produced when specific atoms or ions in the stellar atmosphere absorb light at precise wavelengths. The pattern of lines acts as a fingerprint, identifying both the chemical composition of the stellar atmosphere and its temperature. The spectral classification system, organized into the sequence O, B, A, F, G, K, M from hottest to coolest, revealed that stars come in a wide range of temperatures, and that temperature correlates strongly with color, luminosity, and mass. Our Sun is a G-type star, and Alpha Centauri A is also G-type, slightly hotter and more luminous. Alpha Centauri b is K-type, cooler and dimmer. Proxima Centauri is M-type, the dimmest and most numerous stellar class. The Hertzsprung-Russell diagram, developed in the early 1900s independently by Danish astronomer Ejnar Hertzsprung and American astronomer Henry Norris Russell, plotted stellar luminosity against surface temperature and revealed a striking pattern. Most stars, including all three in the Alpha Centauri system, fall along a diagonal band called the main sequence. The position of a star on the main sequence tells you its mass, and its mass determines nearly everything else about its life cycle. Main sequence stars fuse hydrogen in their cores. The more massive the star, the hotter and brighter it burns, and the shorter its life. A star like Alpha Centauri A, slightly more massive than our Sun, will exhaust its core hydrogen and evolve off the main sequence in somewhat less time than our Sun. A red dwarf like Proxima Centauri burns its hydrogen so slowly and uniformly that it may spend trillions of years on the main sequence before its fuel is depleted. The fact that all three stars in the Alpha Centauri system are on the main sequence and that they are all of similar age tells us they formed from the same cloud of gas and dust at approximately the same time. Star formation typically produces multiple stars from a single collapsing molecular cloud because the collapse tends to fragment rather than producing a single object. This is why multiple star systems are extremely common in the galaxy, with estimates suggesting that half or more of all stellar systems contain at least two stars. The Alpha Centauri system is therefore quite typical in being a triple system. What is atypical is only how close it is to us. From a statistical standpoint, we would expect there to be a triple system within a few light-years of any given star, simply based on how common such systems are. We just happen to have one in our immediate neighborhood. This raises an interesting cosmological question. If our immediate stellar neighborhood contains one triple system within 5 light-years, and if this is roughly representative of the galaxy as a whole, then we might estimate that the Milky Way contains tens of billions of triple stellar systems. Many of these would contain red dwarfs, which we now know can host rocky planets. The potential number of worlds in the galaxy is staggering. But planets are only part of the story. Chemistry is at least as important. For life to develop, a world needs not just liquid water, but also a supply of the basic chemical building blocks of biology. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are the primary elements of known life. These elements are all common throughout the universe. They are produced in stellar interiors and dispersed into space when stars end their lives. Every star-forming region in the galaxy contains them in abundance. The question of whether the raw materials for life exist at Alpha Centauri is therefore probably not the limiting factor. Carbon and nitrogen and oxygen are everywhere. The limiting factors are more likely related to the stability of planetary environments over the timescales needed for biology to develop and persist. Life on Earth appears to have originated within the first billion years of Earth's existence, approximately 3.5 to 4 billion years ago, based on the oldest known fossils and molecular biological analysis of ancient lineages. That is a relatively rapid emergence by the standard of Earth's total age, but complex multicellular life did not appear until much later, around 600 million years ago. And sophisticated animal life with nervous systems capable of cognition required even longer. This timeline implies that even if Proxima b, or any other nearby world, managed to host early microbial life, the emergence of complex organisms depends on billions of years of stable conditions. A red dwarf's habit of erupting with flares may have disrupted or slowed biological evolution on any world in its system. Alternatively, if life managed to adapt to the radiation environment, the enormous lifespan of red dwarfs could provide incomprehensibly long stretches of stable starshine within which evolution could operate. The origin of life itself remains one of the deepest unsolved problems in science. We do not know precisely how the first self-replicating molecules formed from non-living chemistry on early Earth. The Miller-Urey experiment in 1953 demonstrated that organic molecules, including amino acids, can form from simple gases under the influence of energy. But the gap between amino acids and a living cell is vast and still not fully bridged by any accepted theory. Several hypotheses exist. The RNA world hypothesis proposes that early life used RNA both to store genetic information and to catalyze chemical reactions before the division of labor between DNA and proteins evolved. Hydrothermal vents on the ocean floor are proposed as sites where the chemistry of life might have first concentrated and combined. Some researchers have suggested that life's origins may involve clay minerals as templates, or that life began in shallow surface pools, subjected to cycles of wetting and drying. None of these hypotheses are fully confirmed. What they share is the implication that life needs both chemistry and energy, and that given the right conditions, the chemistry of life tends to happen. If that implication is correct, then any world with liquid water and a source of chemical energy has the potential to develop life, whether it orbits a G-type star, a K-type star, or an M-type red dwarf. The study of extremophiles, organisms that thrive in conditions once thought hostile to life, has dramatically expanded our conception of the range of environments that can support biology. Thermophilic bacteria live in boiling hot springs and hydrothermal vents at temperatures well above 100 degrees Celsius. Psychrophilic organisms grow in the frigid brine channels within Arctic sea ice. Acidophiles flourish in highly acidic environments. Halophiles live in saturated salt solutions. Radio-resistant organisms like Deinococcus radiodurans can survive radiation doses thousands of times larger than what would kill a human. The study of these extremophiles has direct relevance to thinking about Alpha Centauri's planets. If life can survive intense radiation on Earth, perhaps it could survive or adapt to the flare environment of Proxima Centauri. If life can thrive in sub-freezing brine, perhaps it could exist somewhere on the cold night side of a tidally locked world where geothermal heat maintains a liquid zone. The boundaries of the habitable zone are far less rigid when we consider the full range of environments that biology can occupy. The field of astrobiology, which combines astronomy, biology, chemistry, geology, and planetary science to study the potential for life beyond Earth, has grown substantially in recent decades. It is not yet the study of confirmed extraterrestrial life, because no such life has been detected. It is the study of what conditions life requires, how those conditions might be met elsewhere, and how we could detect life if it exists. The Alpha Centauri system sits at the center of astrobiological interest for precisely the reasons that make it interesting to astronomers generally. It is close enough to study in detail. It has planets. It has the right chemistry. And it provides a testable environment for the questions that astrobiology is trying to answer. Detecting biosignatures in exoplanet atmospheres would constitute one of the most profound scientific discoveries in human history. The identification of oxygen, ozone, methane, or nitrous oxide in specific combinations that cannot easily be explained by non-biological processes would be taken as strong, though not definitively conclusive, evidence of life. On Earth, the presence of oxygen in our atmosphere is almost entirely the product of photosynthetic life. Without constant biological replenishment, oxygen would quickly react with surface minerals and disappear from the atmosphere. However, interpreting atmospheric spectra is complicated. False positive signals, where abiotic processes produce the same chemical fingerprints as life, are possible. Very careful analysis and multiple independent lines of evidence would be required before any credible announcement of a biosignature detection could be made. The scientific community has thought carefully about the protocols for announcing and verifying potential biosignature detections. Given the extraordinary implications, the bar for evidence must be correspondingly high. A single unusual spectral feature in one observation would not be sufficient. Reproducibility, independence, and the elimination of alternative explanations would all be required. The question of whether we are alone in the universe is one of the oldest and most profound questions humanity has ever asked. Every generation has asked it in the context of the knowledge available to them. Before the Copernican revolution, it was a philosophical and theological question about the uniqueness of creation. After the development of telescopes, it became a question about whether other planets existed. In the 20th century, it became a question about whether nearby planetary systems might harbor life. In the 21st century, it is becoming a question that may be answerable through real physical measurements. Alpha Centauri is not just our closest stellar neighbor. It is the nearest place where we can begin to gather actual empirical data relevant to this ancient question. That is the deepest reason for the attention we pay to this system. The timescales involved in all of this are worth dwelling on. The light we see from Alpha Centauri tonight left those stars more than 4 years ago. In that time, a human infant could have learned to walk and talk. Several space missions have been launched. Thousands of scientific papers have been published about exoplanets. The universe does not rush. When breakthrough starshot probes are eventually launched, assuming the technology matures, the first data from the Proxima Centauri system would not arrive for more than 25 years after launch. Plans made today would be carried to fruition by scientists who are currently children. The scientific questions being framed now would be answered by researchers who have not yet chosen their field of study. This long timescale is not unusual in science, nor even in space exploration. The Voyager probes were launched in 1977 and are still returning data today, nearly 50 years later. The data they sent from the outer solar system in the 1980s took many years of analysis to fully interpret. The Hubble Space Telescope, launched in 1990, is still producing scientific results. Major scientific instruments routinely outlive the careers of the scientists who built them. For interstellar exploration, this multi-generational timescale is even more pronounced. The civilization that eventually receives detailed images and atmospheric spectra from Proxima Centauri b may be quite different from the civilization that launched the mission. That is not a reason not to try. It is a reason to appreciate the profound depth of commitment that interstellar science requires. It is also worth considering what we might learn from a null result. If detailed observations of the Alpha Centauri system eventually establish beyond doubt that none of its planets host life, that too would be scientifically and philosophically significant. The closest stellar system to our Sun, containing at least 2 confirmed rocky planets and potentially several others, would be definitively uninhabited. Depending on the reasons, whether atmospheric erosion, radiation, the wrong chemistry, or simple chance, that conclusion would constrain our models of how common life is in the universe. The Drake equation, formulated by astronomer Frank Drake in 1961, attempted to estimate the number of technologically advanced civilizations in our galaxy. It expressed the answer as a product of many factors, including the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life actually develops, and so on. Each factor in the equation is poorly constrained, with estimates ranging over many orders of magnitude. Observations of the Alpha Centauri system could eventually constrain several of these factors. If a planet in the habitable zone of Alpha Centauri A or B is confirmed, it would increase confidence in the fraction of Sun-like stars with potentially habitable planets. If biosignatures are detected or definitively absent, it would constrain the fraction of habitable worlds that actually develop life. Every piece of empirical data we collect about nearby stellar systems contributes to our estimate of life's prevalence in the universe. The more systems we can characterize in detail, the tighter our constraints become. Alpha Centauri, because it is the closest and therefore the most detailed example we have, carries disproportionate weight in these calculations. The history of astronomy is filled with moments when the universe turned out to be much larger, older, or more densely populated than previously imagined. The discovery that our Sun is not at the center of the galaxy, confirmed in the early 20th century. The discovery that our galaxy is one of billions, established in the 1920s. The discovery that the universe is expanding and that the expansion is accelerating, revealed in the 1990s. The discovery that virtually every star appears to have planets, emerging from Kepler data in the 2010s. Each of these moments expanded the potential arena for life. Each one suggested that the conditions needed for biology are not rarities, but commonplaces. The current era, in which we are beginning to characterize the atmospheres and surfaces of rocky exoplanets, may be building toward another such moment. We do not know what we will find when we study Alpha Centauri's planets in detail. The universe has a history of exceeding expectations in both directions. Some things we feared were common have turned out to be rare. Some things we assumed were rare have turned out to be ubiquitous. Any confident prediction about what Alpha Centauri holds would be premature. What is not premature is recognizing that we are at the beginning of the era in which these questions can be addressed empirically rather than philosophically. The instruments exist, or are being built. The missions are being designed. The mathematical frameworks for interpreting the data are being developed and tested. The Alpha Centauri system will not keep its secrets forever. The light from those 3 stars has been traveling to Earth for over 4 years. We have been reading that light with increasingly sophisticated instruments for decades. In the coming decades, we will read it with tools that can distinguish the signatures of oxygen and methane in the atmosphere of a world the size of Earth, orbiting 4 light-years away. Whatever those measurements reveal, they will expand what we know about where life can exist, and perhaps where it does. And in doing so, they will change our understanding of what it means to be inhabitants of this particular corner of a very large and very old universe. The mechanics of how we detect planets around distant stars deserve a more complete explanation, because the methods themselves are fascinating, and each one illuminates a different aspect of exoplanet science. Before any exoplanet was confirmed around a main sequence star, the primary evidence for planetary systems came from indirect sources. Observations of circumstellar disks, clouds of gas and dust orbiting young stars, showed that the raw materials for planet formation were common. The presence of chemical signatures in stellar atmospheres suggested that some stars had accreted material from planetary bodies. Theoretical models showed that the processes that formed our solar system should operate around other stars as well. The breakthrough came with the radial velocity method, sometimes called the Doppler spectroscopy method. When a planet orbits a star, the planet and star actually orbit their common center of mass. For a very massive planet like Jupiter, this center of mass can lie outside the body of the star itself, and the star traces a noticeable circular or elliptical path in space. For smaller planets, the effect is much subtler, but it still causes the star to wobble slightly back and forth along our line of sight. When the star moves toward us, its light is blue shifted, meaning the spectral lines shift toward shorter wavelengths. When it moves away from us, the light is red shifted toward longer wavelengths. By measuring these tiny shifts with extreme precision, astronomers can infer the presence and mass of orbiting planets. The radial velocity method is especially sensitive to massive planets in close orbits because these produce the largest stellar wobbles. The first confirmed exoplanet around a main sequence star, 51 Pegasi b, detected in 1995 by Michel Mayor and Didier Queloz, was found this way. It was a gas giant roughly half the mass of Jupiter, orbiting incredibly close to its star with a period of just 4 days. Nothing in our solar system remotely resembles this configuration, which is why the discovery was initially controversial. Theorists had assumed that large gas giants could only form far from their stars, where temperatures are cold enough for ices to condense and provide extra building material. The discovery forced a revision of planet formation theory. Computer simulations eventually showed that gas giants can form farther out and then migrate inward through interactions with the protoplanetary disk. This process of planetary migration became a central concept in planetary science, with profound implications for how planetary systems are arranged. If planetary migration is common, then the arrangement of planets in any given system might look quite different from its initial configuration. Planets that formed at one orbital distance might end up at quite another. Migration can cause planets to be ejected from the system entirely, or to collide with each other, or to end up in orbital configurations we would not have predicted from initial conditions. For the Alpha Centauri system, migration is an important consideration. Even if planet formation occurred efficiently around Alpha Centauri A or B, the final positions of any planets that formed might have been substantially altered by migration, gravitational interactions between planets, and perturbations from the companion star. Predicting where planets should be now, based only on where they should have formed, is not reliable. The transit method, used so effectively by the Kepler Space Telescope and its successor, TESS, the Transiting Exoplanet Survey Satellite, works differently. It detects the slight dimming of a star's light when a planet passes in front of the star from our viewing angle. The amount of dimming tells us the ratio of the planet's area to the star's area, giving us the planet's radius. The frequency of the dimming tells us the planet's orbital period. Transit detections have found thousands of exoplanets and revealed that planets come in an astonishing range of sizes, from smaller than Earth to several times the size of Jupiter. They have also revealed that the most common type of exoplanet in our galaxy appears to be super-Earths and mini-Neptunes, planets in the size range between Earth and Neptune that have no analog in our own solar system. The absence of planets in our solar system in this size range has puzzled planetary scientists. Why does our solar system lack super-Earths? Current thinking suggests that in our solar system, Jupiter's early formation and possible inward migration may have disrupted the formation of inner rocky planets, preventing them from growing beyond terrestrial sizes. In systems without a Jupiter analog, Inner super-Earths and mini-Neptunes form readily. Whether the Alpha Centauri system has a Jupiter-like giant planet in a wide outer orbit is not yet known. Such a planet, if it exists, would affect the stability of interplanetary orbits and the delivery of comets and asteroids to inner planets. In our own solar system, Jupiter's gravitational influence redirects many outer solar system objects, sending some toward the inner system and deflecting others away. This has had a complex and still debated effect on the frequency of large impacts on Earth. Large impacts played a crucial role in early Earth's history. The leading hypothesis for the formation of the Moon holds that a Mars-sized body collided with the proto-Earth about 4.5 billion years ago, ejecting material that coalesced into the Moon. This collision may also have contributed to Earth's relatively fast rotation rate and the large axial tilt that drives our planet's seasons. Without that collision, Earth might be a very different world. The Moon itself plays a stabilizing role in Earth's axial tilt over geological timescales. Without the Moon's gravitational influence, Earth's axial tilt might vary chaotically, producing dramatic changes in climate that could disrupt the long-term stable conditions that complex life may require. Whether planets in the Alpha Centauri system have similar stabilizing companions is unknown. These kinds of contingent factors, the presence of a large outer planet, the occurrence of specific large impacts, the existence of a stabilizing moon, remind us that Earth's particular configuration may not be easily replicated. Life might need specific conditions beyond just liquid water and the right temperature, or life might be far more adaptable than we assume, capable of arising and evolving even under significantly different conditions. The study of planetary geology and geochemistry on Earth has revealed how deeply planetary interiors and surfaces interact with the chemistry of life. Plate tectonics, the slow movement of crustal plates that produces mountain ranges, volcanic activity, and seafloor spreading, has played a critical role in regulating Earth's climate over billions of years. The carbon silicate cycle, in which carbon dioxide is drawn from the atmosphere by rainfall and chemical weathering of rocks, carried into the ocean, and eventually returned to the atmosphere by volcanic activity, acts as a long-term thermostat that has kept Earth's climate relatively stable despite changes in solar luminosity. Whether rocky planets around other stars have plate tectonics is not known. Plate tectonics requires specific conditions of planetary size, composition, temperature, and water content. Mars, for example, appears to lack active plate tectonics, though it shows evidence of past volcanic activity. Venus has no plate tectonics either. Earth may be unusual even within our own solar system in having this crucial climate-regulating mechanism. For Proxima Centauri b, or any rocky planet in the Alpha Centauri system, the presence or absence of plate tectonics would significantly affect the long-term habitability of the world. Without the carbon silicate cycle, or an equivalent geochemical feedback mechanism, a planet might experience runaway warming or cooling that permanently removes it from habitable conditions, even if it started in a favorable zone. The interplay of geology, atmosphere, and astronomy makes habitability a genuinely interdisciplinary problem. No single measurement or observation can settle the question for any world. It requires understanding the planet's interior, its surface processes, its atmospheric composition and dynamics, its relationship with its star, and the history of all of these over billions of years. The most exciting scientific developments in exoplanet research over the past decade have been in atmospheric characterization. For hot Jupiters, gas giants orbiting very close to their host stars, atmospheric studies have revealed exotic chemistries unlike anything in our solar system. Temperatures on the day side of some hot Jupiters exceed 2,000 degrees Celsius, hot enough to vaporize iron. Winds on these worlds may blow at speeds of several kilometers per second. Some show evidence of clouds made of silicate particles, or even titanium dioxide. These extreme environments are scientifically fascinating precisely because they are so different from anything we can study in our solar system. They test atmospheric models under conditions of high temperature, intense radiation, and strong tidal forces in ways that expand our theoretical understanding. And while no one expects life on a hot Jupiter, understanding how atmospheres work on these worlds builds the tools and models needed to eventually characterize the atmospheres of smaller, cooler, more potentially habitable worlds. The characterization of rocky exoplanet atmospheres is a much harder problem. A rocky planet is smaller and therefore blocks less starlight when it transits. Its atmospheric signals are proportionally much fainter. For a planet like Proxima b, which does not even transit its star from our viewpoint. Transit spectroscopy is unavailable. Alternative methods, like direct imaging and reflected light spectroscopy, are the primary routes forward for non-transiting worlds. The concept of direct imaging of exoplanets requires suppressing the blinding glare of the parent star by a factor of roughly 10 billion or more. The light from a sun-like star outshines the reflected light of an Earth-sized planet in the habitable zone by this staggering ratio. This is the equivalent of trying to photograph a firefly sitting next to a lighthouse from a great distance. Two primary techniques are being developed. A coronagraph is an opaque disk placed inside a telescope to block the central star's light, analogous to covering the sun with your thumb to see objects near it. A starshade is a separately flying spacecraft, shaped like a flower petal, positioned thousands of kilometers in front of the telescope to block the star's light before it enters the telescope at all. Both approaches are being pursued in parallel, with different advantages and engineering challenges. The Habitable Worlds Observatory, recommended by a major decadal survey of the astronomy community in 2021 as the highest priority flagship mission for the coming decade, is conceived as a large space telescope with direct imaging capability designed specifically to search for life signatures in the atmospheres of nearby rocky exoplanets. If built and launched on the timelines currently envisioned, it could conduct detailed atmospheric studies of nearby habitable zone planets, including any that might be found around Alpha Centauri A and B, within the next several decades. This mission concept represents the culmination of decades of theoretical, technological, and observational groundwork. The detection of exoplanets, their atmospheric characterization, the development of coronagraph and starshade technology, the theoretical modeling of biosignature gases and their false positives, all feed into the design of a mission that could actually detect signs of life in another stellar system. The stakes of that search cannot be overstated. A confirmed detection of atmospheric biosignatures on an exoplanet would be one of the most transformative discoveries in the history of science. It would tell us that Earth is not unique in its capacity to generate and sustain life. It would have profound implications for our understanding of biology, chemistry, planetary science, and our place in the universe. A confirmed absence, on the other hand, after thorough searches of the most promising targets, would be equally significant. It would suggest that life, even microbial life, is genuinely rare, and that Earth occupies an extremely unusual position in the cosmos. Neither result would close off the question entirely, but either would mark a fundamental turning point in human self-understanding. The Alpha Centauri system will feature prominently in this search. Its proximity means that any habitable zone planets there, if they exist, would be among the most accessible targets for detailed atmospheric study. The brightness of Alpha Centauri A and B means that their light reflected off planetary surfaces would be relatively intense by exoplanet standards, making spectroscopic characterization somewhat easier. And the existing inventory of planets in the Proxima system gives researchers specific targets around which to design observations. Proxima Centauri b, with its proximity and Earth-like mass estimate, will likely be among the highest priority targets for future biosignature searches, despite the challenges posed by its non-transiting geometry and its host star's flare activity. If future measurements can constrain its atmospheric composition at all, even placing upper limits on certain gases would be scientifically informative. The question of whether Proxima b has retained an atmosphere against the assault of Proxima's flares is itself addressable by future X-ray and ultraviolet observations of the star. By characterizing the frequency, intensity, and energy distribution of Proxima's flares with high precision, researchers can model the rate at which atmospheric gases are sputtered away by stellar particles over time. Combined with models of planetary magnetic field generation, these calculations can estimate whether atmospheric retention over billions of years is plausible for Proxima b. Early results from flare monitoring campaigns have been mixed. Some observations have caught Proxima Centauri in dramatic flaring events, with ultraviolet fluxes spiking to hundreds of times their quiescent levels. These events, if typical, could make Proxima b's surface extremely hostile. Other periods of observation show the star in relative quiet. Understanding the statistical distribution of flare magnitudes and frequencies over long baselines is crucial for making reliable habitability assessments. The timescale over which a planet can retain its atmosphere depends also on the planetary mass, the strength of its gravity, and the atmospheric temperature. Heavier atoms and molecules are harder for a planet to lose because they require more energy to reach escape velocity. A planet slightly larger than Earth, as Proxima b may be, would have stronger gravity and might retain heavier atmospheric components like carbon dioxide and nitrogen, even if lighter gases like hydrogen and helium escape. An atmosphere composed primarily of carbon dioxide and nitrogen would not be one we would find comfortable, but it could still maintain surface temperatures through the greenhouse effect and provide pressure sufficient to allow liquid water in some regions. Mars once had a denser carbon dioxide atmosphere, and early Mars may have had liquid water on its surface. Exactly when and how Mars lost most of its atmosphere is still an active research topic, with implications for understanding atmospheric loss at other worlds. The comparison to Mars is instructive. Mars sits within what would be considered the outer edge of our Sun's habitable zone. It is about half the diameter of Earth and roughly 1/10 the mass. Its lower gravity means it retains its atmosphere less efficiently. Its distance from the Sun means even a carbon dioxide greenhouse effect cannot warm it sufficiently to maintain widespread surface liquid water today. And its lack of a global magnetic field means its atmosphere is gradually eroded by the solar wind. Proxima b is more massive than Mars. Its gravity is stronger, but its host star is far more active in the relevant radiation regimes. The net effect on atmospheric retention is unclear, without detailed models tailored to Proxima b's specific conditions. The scientific community has developed increasingly sophisticated computer models for simulating exoplanet atmospheres and their interaction with stellar environments. These models can track the chemistry of atmospheric gases, the circulation of winds, the transport of heat from the day side to the night side on tidally locked worlds, and the effect of stellar radiation on atmospheric layers at different altitudes. One class of models, called global climate models, was originally developed for studying Earth's climate and has been adapted for exoplanet applications. By adjusting parameters like planetary mass, atmospheric composition, orbital distance, and stellar luminosity, researchers can explore how different conditions affect the climate of hypothetical worlds. Some of these models have been applied specifically to Proxima b and have produced a wide range of results depending on the assumed parameters. Some models suggest that a Proxima b with an Earth-like atmosphere could maintain liquid water on a portion of its surface, particularly around the substellar point, the region that permanently faces the star. Under these conditions, the planet might support a stable liquid water ocean in its hot center and frozen ice caps in the permanent night region. The atmospheric circulation would be complex, with winds driven by the persistent day-night temperature contrast rather than the day-night cycle that drives weather on Earth. Other models suggest that without a specific combination of atmospheric composition and pressure, Proxima b would either freeze solid or experience atmospheric collapse. Atmospheric collapse can occur on tidally locked worlds if carbon dioxide in the atmosphere freezes out on the cold night side, reducing the greenhouse effect until the entire planet reaches sub-freezing temperatures. Whether this happens depends critically on the total atmospheric mass and composition. These modeling results illustrate why the question of Proxima b's habitability cannot be resolved without actual observational constraints on the planet's atmospheric properties. The models are only as good as their assumptions. Different assumptions produce different climates. Only data can break the degeneracy. The history of Mars research provides a useful cautionary lesson. Early telescopic observations led to significant enthusiasm about the possibility of Martian life. Percival Lowell's famous observations in the late 19th and early 20th centuries, which he interpreted as artificial canals, inspired both scientific speculation and cultural imagination about Martian civilization. Subsequent better observations, and eventually spacecraft missions to Mars, gradually replaced this picture with one of a cold, dry, geologically quiet world with a thin atmosphere and no apparent life. But even this more accurate picture has continued to evolve. Mars orbiters have found evidence of extensive past water. Mars landers have measured the chemistry of rocks formed in the presence of liquid water. Mars rovers have found organic molecules and evidence of seasonal methane variations that are not yet fully explained. The picture of Mars continues to accumulate complexity and unexplained phenomena. The lesson is that direct observation consistently reveals more than theoretical expectation, and often more complexity and nuance than simple models predict. The same will almost certainly be true of Alpha Centauri's worlds. Whatever we find there, and we will eventually find something, it will not simply confirm our prior expectations. It will challenge and expand our models. This is why the scientific investment in studying the Alpha Centauri system is justified not just by the possibility of finding life, but by the certainty of finding scientifically rich and unexpected complexity. Planets are not simple objects. They are dynamic systems with geology, chemistry, atmospheric physics, and potentially biology, all interacting over billions of years. Every planet we study in detail teaches us something about how planetary systems work that we could not have learned from theory alone. Our own solar system has provided the bedrock of planetary science. Mars, Venus, Jupiter, Saturn, and their moons have each contributed distinct lessons. Mercury's unusual iron core composition challenged models of planet differentiation. Venus's runaway greenhouse effect illustrated how dramatically a planet similar in size to Earth can diverge in climate history. Europa's subsurface ocean expanded the definition of potentially habitable environments in our solar system. Titan's thick nitrogen atmosphere and methane lakes provided a case study in organic chemistry under conditions very different from Earth's. The worlds of the Alpha Centauri system will add their own chapters to this growing library of planetary science. Even if none host life, they will inform our understanding of how rocky planets form and evolve in binary stellar systems, how red dwarfs interact with their closest companions, and how the diversity of planetary environments is distributed across different types of stellar neighborhoods. Science progresses in iterative cycles of observation, hypothesis, prediction, and testing. The Alpha Centauri system is entering an era of increasingly detailed observational scrutiny. Each new data point adds a constraint. Each constraint eliminates some hypotheses and focuses attention on others. The converging web of measurements is gradually resolving a picture that was, as recently as a generation ago, almost entirely blank. When the first tentative signal of a planet around Proxima Centauri was announced in 2016, it was the result of more than 400 observational measurements taken over 15 years. The confirmation 2020 required an additional instrument of even greater precision and years more of data. The slow accumulation of evidence, carefully checked and independently verified, is the reliable mechanism through which science advances. Alpha Centauri will continue to yield its secrets at this pace, not in dramatic single announcements, but in the steady accumulation of measurements that gradually narrow the range of what is possible. That process is already underway, and it will continue for decades. The 4 light-years of space between us and this triple stellar system is not an obstacle to knowledge. It is the medium through which knowledge travels, carried by light from those distant suns to our waiting instruments. We have been receiving and reading that light for as long as we have had eyes. With better tools, we read it more clearly and find more within it. Every photon that reaches us from Alpha Centauri A, Alpha Centauri B, and Proxima Centauri carries information about the physical state of those objects. The temperature of stellar surfaces, the composition of stellar atmospheres, the presence of stellar flares, the motion of planets in orbit, the reflection of starlight off planetary surfaces, all of this is encoded in the light. Our instruments are increasingly sophisticated decoders. The universe has been sending us this message for the entire history of life on Earth. We have only recently developed the tools to begin reading it in earnest. And the message it carries about our nearest stellar neighbors is turning out to be far richer and more detailed than anyone imagined when Henderson first measured the parallax of that bright southern star nearly 2 centuries ago. The infrastructure of modern astronomy that makes this research possible is itself a remarkable achievement of engineering and international cooperation. The Very Large Telescope, operated by the European Southern Observatory in Chile's Atacama Desert, consists of 4 main telescopes, each with a mirror 8.2 meters across, that can work individually or be combined into an interferometer of extraordinary resolving power. At its location on Cerro Paranal, at an altitude of 2,635 meters, the air is exceptionally clear and dry, providing some of the best astronomical seeing on Earth's surface. The Atacama Desert receives so little rainfall and has such stable atmospheric conditions that it has been chosen as the site for multiple major international observatories. The instruments mounted on the Very Large Telescope include ESPRESSO, which we mentioned in the context of Proxima b confirmation, as well as SPHERE, an instrument designed for direct high-contrast imaging of planets and disks around nearby stars, and GRAVITY, which uses interferometry to achieve resolution approaching that of a telescope 800 meters across. Together, these instruments provide capabilities across a range of exoplanet science applications. The future Extremely Large Telescope, also being built in the Atacama by the European Southern Observatory, will have a segmented primary mirror 39 meters in diameter. It is designed specifically with the capability to directly image large exoplanets and characterize their atmospheres, and may extend to rocky planets in favorable cases. Its enormous light-gathering area and advanced adaptive optics systems, which correct for atmospheric turbulence in real time, will provide a qualitative leap in capabilities over current instruments. Adaptive optics systems use deformable mirrors whose shape can be adjusted hundreds of times per second to compensate for the blurring caused by atmospheric turbulence. Without adaptive optics, even the largest ground-based telescope is limited in resolution by the boiling motion of the atmosphere. With adaptive optics, a large telescope can approach its theoretical diffraction-limited resolution, comparable to or exceeding what is achievable from space with a smaller mirror. The technology of adaptive optics was actually developed initially for military reconnaissance applications, where it was used to sharpen satellite imagery from ground-based telescopes observing artificial satellites. The technology was declassified and transferred to astronomy in the 1990s, enabling a revolution in ground-based optical astronomy. This kind of technology transfer, from military applications to scientific research, has occurred multiple times in the history of modern astronomy. Space-based telescopes avoid atmospheric turbulence entirely, but come with their own constraints. The difficulty and expense of launching large instruments into space limits the mirror sizes achievable in orbit. The James Webb Space Telescope, with its 6.5-meter primary mirror, is the largest space telescope currently in operation, and it required extraordinarily complex engineering involving a mirror that folds for launch and deploys in space. Future space telescope concepts for exoplanet science include the Habitable Worlds Observatory, estimated to require a primary mirror in the roughly 6 to 8 meter range, equipped with a sophisticated coronagraph. Its design draws on lessons from the Roman Space Telescope, a more near-term mission with advanced coronagraph capabilities, and from the Nancy Grace Roman Space Telescope's wide-field surveys. The Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field surveys to find thousands of additional exoplanets through microlensing, a gravitational lensing effect that amplifies the light of background stars when a foreground object, including planets, passes in front of them. Microlensing is especially sensitive to planets at intermediate orbital distances from their stars, complementing the radial velocity and transit methods that are most sensitive to close-in planets. Together, these facilities will provide a comprehensive picture of the population of planets around nearby stars, constrain the frequency of Earth-like planets in habitable zones, and begin to characterize the atmospheric chemistry of the most accessible examples. The Alpha Centauri system will be a central and recurring target in this program of observations. It is also worth considering what we mean by the term habitable in the context of the history of Earth itself, because Earth's habitability has not been constant over its 4.5 billion year history. The early Earth, in the first few 100 million years after formation, was an extremely hostile environment by modern standards. The surface was bombarded by large impactors, asteroids, and comets left over from the formation of the solar system. The atmosphere was thick with carbon dioxide, methane, and other gases, with very little free oxygen. The oceans were probably warm, acidic, and chemically rich. Ultraviolet radiation from the young sun was intense, and without an ozone layer, it penetrated to the surface. And yet, evidence suggests that life appeared very early in Earth's history, possibly within the first billion years. The earliest confirmed microfossils date to roughly 3.5 billion years ago, and chemical signatures that may indicate biological activity have been found in rocks up to 4 billion years old. Life apparently arose very quickly in geological terms, even under conditions that would be thoroughly inhospitable to most modern organisms. This early appearance of life suggests that the origin of life is not an extraordinarily improbable event requiring billions of years of chemical preparation. Given the right raw materials and energy sources, the transition from chemistry to biology may happen relatively readily. If this interpretation is correct, it implies that life is not just possible on other worlds, but perhaps common, given suitable planetary environments. The period from roughly 2.4 billion years ago is known as the Great Oxidation Event. Before this point, Earth's atmosphere contained essentially no free oxygen. Photosynthetic cyanobacteria had been producing oxygen as a metabolic byproduct for some time, but it was being consumed by reactions with reduced minerals in rocks and oceans. When the reduced mineral buffer was finally exhausted, oxygen began to accumulate in the atmosphere. This was a catastrophe for the anaerobic life forms that dominated early Earth, for whom oxygen is toxic, but it opened the door for aerobic metabolism, which is far more energetically efficient. The energy available to aerobic organisms enabled far more complex biochemistry, eventually leading to the development of eukaryotic cells and subsequently multicellular life. The evolution of complex life on Earth thus depended not just on liquid water and a stable temperature, but on a specific sequence of biological and geochemical events that took billions of years to unfold. Whether analogous sequences would occur on other worlds is entirely unknown. The conditions that allowed the Great Oxidation Event on Earth may not be replicated elsewhere, or they may be common wherever photosynthetic life evolves. We simply cannot know without more data. The search for biosignatures in exoplanet atmospheres would ideally detect oxygen or ozone, since these are strongly tied to photosynthetic life. But even if photosynthesis does not arise everywhere, other metabolic strategies could produce different atmospheric signatures. Methane produced by methanogenic microbes, nitrous oxide produced by denitrifying bacteria, or the specific combinations of gases that are thermodynamically disequilibrium signatures of life, all offer potential detection pathways. The concept of thermodynamic disequilibrium as a biosignature is particularly elegant. In the absence of life, a planet's atmosphere gradually approaches chemical equilibrium, with different reactive species neutralizing each other over time. Life continually pumps the atmosphere away from equilibrium by consuming some chemicals and releasing others. Earth's atmosphere contains both oxygen and methane simultaneously, two gases that should react with each other on the timescale of thousands of years if nothing were maintaining their levels. The simultaneous presence of both is a strong indicator that biological processes are actively replenishing them. Detecting such a disequilibrium signature in the atmosphere of a planet in the Alpha Centauri system would require extreme observational precision, but the physics of spectroscopy shows it is not fundamentally impossible. It requires a large enough telescope, a long enough integration time, and a quiet enough stellar environment that the signal does not drown in the noise of stellar variability. The path from where we are today to where we need to be for such a measurement runs through many intermediate steps. Each step produces scientific results of its own, not just progress toward the final goal. The characterization of stellar activity at Alpha Centauri, the detection of additional planetary candidates, the modeling of atmospheric retention scenarios, the testing of coronagraph technology, all of these are scientifically valuable in themselves and also build the foundation for the eventual atmospheric biosignature search. Science rarely proceeds in straight lines. The history of exoplanet research has included false starts, retracted detections, revised mass estimates, and debates over interpretation that sometimes lasted years. The field has matured significantly in its methodology and its standards of evidence. The false alarm probability of modern planet detections is rigorously quantified. Multiple independent verification is increasingly required before a planet is added to confirmed catalogs. This maturity is itself a scientific achievement. The ability to distinguish real signals from instrumental artifacts, stellar variability from planetary signatures, and genuine atmospheric features from systematic errors in calibration has been built up through years of experience with many different stars and instruments. The Alpha Centauri system has been both a beneficiary and a contributor to this methodological maturation. The 2012 false alarm around Alpha Centauri b, where a planet signal was later found to be a mathematical artifact, was a painful episode but also a learning experience. It sharpened the community's understanding of how stellar noise can masquerade as planetary signals and led to improved analysis techniques that have benefited the entire field. The 2016 detection of Proxima b, by contrast, withstood multiple years of additional scrutiny and independent verification. The combination of HARPS data, espresso data, and the pale red dot campaign data, each analyzed independently and finding consistent results, established the planet's existence on a much firmer statistical footing. This back and forth of detection, skepticism, and verification is not a sign of scientific confusion. It is the mechanism by which science achieves reliable knowledge. Every idea passes through scrutiny, and only those that survive the scrutiny earn the status of established fact. The alternative, accepting claims on the basis of initial announcements without independent verification, would lead to a far less reliable body of knowledge. As we look ahead to the next phase of Alpha Centauri research, the coming decades will likely see several major developments. Atmospheric characterization efforts will intensify as the extremely large telescope comes online and as instruments like HIRES, the high-resolution Echelle spectrograph planned for the extremely large telescope, begin gathering spectra of exoplanet atmospheres with unprecedented precision. If any rocky world in the Alpha Centauri system transits its star, even partially, from our viewing angle, HIRES and similar instruments could characterize its atmosphere directly. Astrometric missions like the ongoing Gaia satellite survey continue to accumulate positional measurements of nearby stars with micro-arcsecond precision. Gaia's data could reveal the gravitational signatures of planets in the Alpha Centauri system through the tiny wobbles they induce in the stars' paths across the sky. Astrometry is particularly sensitive to planets in long-period orbits that are hard to detect by other methods and could find outer planets in the system that radial velocity surveys have missed. The development of space-based direct imaging missions will mark a step change in what is possible. Even a moderately sized space telescope equipped with a high-performance coronagraph positioned to observe Alpha Centauri could potentially detect reflected light from planets in the habitable zones of Alpha Centauri A and B. Such an observation would not only confirm or deny the existence of these planets, but could begin to characterize their colors, which carry information about surface and atmospheric composition. Technology demonstrator missions, designed to test coronagraph and starshade technologies in space, will precede full-scale science missions and provide crucial engineering data for designing the instruments that will ultimately conduct the most sensitive searches. In parallel, theoretical work will continue to refine our understanding of what observations to expect from different types of worlds. As computational power grows and physical models become more sophisticated, predictions for the appearance of rocky exoplanet atmospheres under various conditions become more precise. Better predictions enable more targeted observations and more sensitive searches for specific signatures. The interplay of observation and theory in this field has been extraordinarily productive. Observational surprises have driven theoretical revisions, and improved theories have guided observers toward new measurements they would not have thought to make without theoretical motivation. This dialogue between observation and theory is the engine of scientific progress in exoplanet science. The Alpha Centauri system sits at the intersection of all these converging developments. It will be a target of every major facility and mission in the coming decades. Every improvement in sensitivity and method will be applied to it. And whatever is found, or not found, will reshape our understanding of the most fundamental questions about life and planets in the universe. For those of us following the science in real time, the years and decades ahead promise to be some of the most scientifically eventful in the history of astronomy. The tools are being built, the methods are being refined, the targets are identified, and the nearest stellar system, that triple gravitational partnership of stars, just over 4 light-years away, is ready to be read in a depth and detail that previous generations of astronomers could only dream of. The stars of Alpha Centauri have shone in the sky for billions of years. For almost all of that time, no mind capable of wondering about them existed anywhere in the universe, as far as we know. Now there are minds that not only wonder, but are actively building the means to answer those wonderings with empirical precision. That transition, from wonder to measurement, is one of the defining achievements of conscious intelligence. Whatever those measurements ultimately reveal about the Alpha Centauri system, they will expand the domain of the known and reduce the domain of the uncertain. They will add to the growing body of knowledge about what kinds of worlds exist in the universe and under what conditions life might arise. And they will do so by reading more carefully than ever before the light that 4 stars, including our own, have been exchanging across the void for billions of years. The context of interstellar communication is worth exploring more fully because it connects the Alpha Centauri system not just to our telescopes and spacecraft, but to our ideas about intelligence itself. The search for extraterrestrial intelligence, commonly known as SETI, has been an ongoing scientific effort since the 1960s. The first formal search, Project Ozma, was conducted in 1960 by Frank Drake using a radio telescope in Green Bank, West Virginia. Drake pointed the telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, both of which lie within about 12 light-years of Earth, and listened for artificial signals in the microwave band. No signals were detected, but the effort launched a scientific tradition. In the decades since, radio telescopes around the world have scanned millions of stars at various frequencies. The famous WOW signal, detected at the Big Ear Radio Observatory in Ohio in 1977, was a brief, strong signal that matched the profile expected for an interstellar transmission, but it was never detected again. Its origin remains unexplained. More recently, SETI has expanded beyond radio frequencies. Optical SETI searches for brief, powerful flashes of laser light that might be used for interstellar communication. Technosignature searches look for anomalous energy use, unusual stellar light curves, megastructures, or other signs of technological civilizations. The concept of technosignature detection represents a broader approach that does not assume extraterrestrial civilizations communicate by any specific method. Alpha Centauri is a natural early target in SETI searches precisely because of its proximity. Any signal originating there would be relatively intense when it arrived here. The round-trip communication time of over 8 years is still far shorter than for any other stellar system at greater distances. If any technological civilization were present in the Alpha Centauri system, we would expect it to be among the easier ones to detect. No such signals have been detected, but the absence of detected signals does not definitively imply absence of intelligence. Our search has been limited in scope, duration, and frequency coverage. The parameter space of possible interstellar signals is vast, and we have explored only a small fraction of it. The Breakthrough Listen initiative, part of the same Breakthrough Initiatives organization behind Breakthrough Starshot, is conducting the most comprehensive SETI search in history. Using some of the world's most powerful radio telescopes and covering a broad range of frequencies and targets, it is systematically surveying the nearest stars, the galactic center, and other high-priority targets for artificial signals. The amount of data collected and analyzed by Breakthrough Listen dwarfs all previous SETI efforts combined. Alpha Centauri has been included in Breakthrough Listen observations. So far, nothing artificial has been detected, but the program is ongoing. The relationship between biological life and technological intelligence is itself uncertain. On Earth, life appeared very early, but technology arose only in the past few thousand years, representing an almost negligible fraction of the 4-billion-year history of life on this planet. Intelligence capable of building technology arose only once in the history of Earth, among the great apes lineage. This suggests that even if life is common, intelligence may be less common, and technology even rarer. Or perhaps intelligence is an emergent property of complexity that arises given enough time and sufficiently stable conditions. The 4,800 million years of life on Earth may have required long periods of relatively stable conditions to allow intelligence to arise. If so, the stability of stellar environments over long timescales is another factor relevant to the emergence of technological civilizations. Red dwarfs, with their trillion-year lifespans, might seem ideal for the development of intelligence given enough time. But the intense early flare activity of young red dwarfs may disrupt the stable conditions needed for biological complexity to develop. Whether the billions of years of relative stability that older red dwarfs like Proxima Centauri eventually achieve is sufficient for intelligence to arise remains completely unknown. The Fermi paradox, named after physicist Enrico Fermi, asks why, given the age of the universe and the apparent abundance of planets, we have not yet detected signs of extraterrestrial intelligence. Various resolutions to this paradox have been proposed, ranging from the argument that intelligent life is genuinely rare to the argument that advanced civilizations deliberately conceal themselves, to the argument that interstellar distances make communication and travel impractical even for very advanced civilizations. The Alpha Centauri system is close enough that even a relatively quiet civilization there would likely have produced radio signals detectable from Earth with our current technology. The fact that we have detected nothing from this system specifically is not conclusive evidence against life there, because the development of radio technology is a recent and perhaps transient phase of any technological civilization's development. But it does constrain the possibilities somewhat. All of these considerations, biosignature searches, SETI, planetary habitability, the development of intelligence, converge on the Alpha Centauri system as the nearest laboratory for addressing some of the deepest questions we can ask. The very fact that our species has developed the capacity to ask these questions, to build instruments, to design missions, and to read the light from distant stars with enough precision to detect a planet's wobble in its star's motion, is itself a phenomenon worth appreciating. The cognitive and technological capacity that allows us to study Alpha Centauri developed over tens of thousands of years of human cultural evolution, itself the product of billions of years of biological evolution, itself the product of planetary formation around a star that formed 4.5 billion years ago from a cloud of gas enriched by previous generations of stars. We are, in the most literal physical sense, material from the universe studying itself. The atoms in the instruments that detected Proxima Centauri b were forged in stellar interiors. The photons that those instruments measured traveled 4.25 light-years through vacuum before interacting with the detector materials. The mathematical models that extracted the planet's properties from the data were developed using the collective cognitive heritage of human civilization going back to Babylonian astronomy. This chain of connections, from stellar nucleosynthesis to human civilization to exoplanet detection, is not poetic embellishment. It is accurate physics and history. And it places the study of Alpha Centauri in the context of a universe that has been, in some sense, organizing itself toward the capacity for self-understanding for its entire 14 billion-year history. Whether the Alpha Centauri system contains minds that are asking similar questions about our Sun is a question we cannot answer. What we can say is that the physical laws that govern their stellar system are exactly the same as those governing ours. The same quantum mechanics that determines atomic energy levels, and therefore spectral lines, and therefore our ability to detect their planets, would govern any chemistry and any biology that might exist there. The universality of physical law is both the foundation of scientific confidence and a deep philosophical point. It means that the conditions for life, as we understand it, if they exist at Alpha Centauri, involve the same chemistry, the same thermodynamics, the same molecular biology that life uses here. The molecules of life, amino acids, nucleotides, lipids, are not peculiarly terrestrial inventions. They form readily under the influence of ultraviolet light and in the chemistry of interstellar clouds. They have been found in meteorites. They have been detected spectroscopically in star-forming regions. The raw materials of life are everywhere. The question is whether the specific combination of environmental conditions that allows those materials to organize into self-replicating, metabolizing, evolving systems is common or rare. The answer to that question depends on understanding worlds like those that may orbit Alpha Centauri's 3 stars in far more detail than we currently possess. That understanding is being built systematically and patiently by astronomers, planetary scientists, astrobiologists, engineers, and theorists who have dedicated their careers to expanding what humanity knows about its nearest stellar neighborhood. The work continues day by day, observation by observation, measurement by measurement. The closest stars to our Sun hold the nearest answers to the oldest questions. Whether those answers eventually reveal that we are alone, or that we are not, the pursuit of those answers is itself one of the most profoundly meaningful endeavors that thinking beings have ever undertaken. And Alpha Centauri, bright enough to see with the naked eye from the southern hemisphere on any clear night, patient enough to have waited billions of years for a civilization capable of wondering about it, continues to shine. Each photon it sends our way is a piece of evidence waiting to be read. With better tools and better understanding, we read more of it every year. The story is far from over. In many ways, it has only just begun. To draw together the threads of what we have covered, it is worth surveying where current research on the Alpha Centauri system stands and what the most immediate scientific priorities are. The immediate observational agenda includes continued radial velocity monitoring of all three stars, with next-generation instruments like Espresso and its successors. These surveys aim to detect the signatures of additional planets, constrain the masses and orbits of known candidates, and build a comprehensive picture of the planetary architecture of the system. Each additional year of monitoring increases the sensitivity to long-period planets and improves the statistical foundation of existing detections. High-contrast imaging campaigns using instruments like SPHERE on the Very Large Telescope are also underway. These campaigns aim to detect the reflected or thermal light of any large outer planets in the system. If a Jupiter mass or larger companion exists in a wide orbit around any of the three Alpha Centauri stars, current instrumentation has a reasonable chance of directly imaging it under favorable conditions. Detailed modeling of stellar activity, particularly the flare behavior of Proxima Centauri, is a high priority for assessing the habitability of Proxima b. X-ray and ultraviolet observatories are critical for this work. The characterization of flare frequency distributions and energy spectra provides inputs to atmospheric loss models that estimate how much atmosphere Proxima b could retain over geological timescales. Astrometric analysis of Gaia data for the Alpha Centauri system continues to improve. When the final Gaia data release is complete and processed, it will provide the most precise measurements of stellar positions and proper motions ever made for these stars, enabling more sensitive detection of planetary companions through their gravitational influence on stellar trajectories. The Ptolemy mission concept, which underwent development planning in Australia, aimed to combine precision astrometry with a novel optical design specifically optimized for detecting Earth-mass planets around Alpha Centauri A and B. Whether this mission advances through development and ultimately launches will depend on funding and programmatic decisions, but it represents the kind of targeted, purpose-built approach that may be necessary to resolve the question of rocky planets in the habitable zones of the solar-type stars in the system. Looking further ahead, the extremely large telescope's first light instruments, and eventually its full suite of science instruments, will provide capabilities that dwarf anything currently available. The combination of its enormous aperture, adaptive optics correction, and high-contrast imaging instruments could, in principle, directly detect and begin characterizing planets in the habitable zones of Alpha Centauri A and B under favorable circumstances. The first decade of extremely large telescope operations, expected to begin in the early 2030s, will be transformative for nearby exoplanet science. Space-based coronagraph missions designed for exoplanet characterization, whatever form they ultimately take and whenever they launch, will push the frontier further. The specific design requirements for a mission capable of detecting biosignatures in the atmosphere of an Earth-like planet in the habitable zone of a nearby star are demanding, but not physically impossible. The technology development work happening now in coronagraph and starshade programs will determine whether such a mission is ready to fly in the coming decades. The Breakthrough Starshot program, meanwhile, will continue to develop the laser propulsion technology, miniaturized probe design, and launch infrastructure needed for a first interstellar mission. The engineering challenges are formidable, and the path from current technology to an operational interstellar launch capability will require decades of sustained effort and significant investment. But the program is structured as a long-term initiative precisely because it recognizes this timescale. None of these developments are guaranteed. Science and technology advance through sustained effort, funding, international cooperation, and the specific decisions of institutions and individuals. Programs are delayed, canceled, redesigned. Discoveries come sometimes sooner than expected and sometimes much later. The future of Alpha Centauri research is not fully determined by the plans being made today. What is determined is the fundamental scientific importance of the questions and the existence of physical principles that make answering them possible. Alpha Centauri A, Alpha Centauri B, and Proxima Centauri will continue to exist and to emit light for longer than any human institution will persist. The questions about their planets, their habitability, and their possible life will remain scientifically addressable as long as intelligent beings with appropriate technology exist on Earth or elsewhere. The accumulation of knowledge about this system has been one of the intellectual achievements of the past century of astronomy. The acceleration of that accumulation in the past decade, driven by improved instrumentation and new detection methods, suggests that the next several decades will bring even more rapid progress. We stand at a genuinely historic moment in the investigation of the Alpha Centauri system. The first confirmed planets have been found. The first dedicated observing campaigns have begun. The next generation of instruments is under construction. The first interstellar mission concepts are in engineering development. The questions that have motivated astronomers for generations are moving from the realm of pure speculation toward empirical resolution. Whatever the universe holds in those 4 light-years of space between our Sun and its nearest stellar companions, we are developing the means to find out. And the finding out, however long it takes and whatever it reveals, will be one of the defining scientific achievements of human civilization. The light from Alpha Centauri travels toward us at the speed of light, crossing 4 years of space to reach our detectors. We have been looking at it for a very long time. We are finally, genuinely, beginning to understand what it is telling us.